Hello, everyone, and welcome to today's webinar. On behalf of American Petroleum Professionals of Iranian Heritage, APPIH, it's our great honor to start another webinar entitled Energy Production and Storage by Dr. Mojdeh Delshad. It's a great honor for us. After 2 years, we have a chance to listen to Dr. Delshad's presentation. Dr. Delshad is a research professor in the Department of Petroleum and Geosystems Engineering at UT Austin. She served as a vice president and the president CEO of the Ultimate EOR Services. Also, she was the assistant director for the Department of Energy Funded Center for Frontiers of Subsurface Energy Security, CCS. She holds a BS degree in chemical engineering from the Sharif University in Iran and master and PhD degree in the petroleum engineering from the UT Austin. She has over 35 years of experience in modeling multi-phase flow and design of chemical and gas recovery methods in both lab and field scales. She has 100 journal publications and 150 papers proceedings. She received the ASP Distinguished Member Award in 2014. Her current research focus includes a modeling key mechanism of CO2 and hydrogen storage in deep saline aquifers and depleted oil and gas reservoir, multi-phase reactive transport, numerical simulator developments, and application to CO2 storage and H2 cyclic injection for both lab and field scale. I would thank Dr. Delshad for accepting our invitation, and without further delay, I'm transferring microphone to her for starting her presentation. Thank you.
Thank you, Hamid Reza. Thank you for organizing this webinar and for your invitation. I'm happy to be here. And I believe Hamid Reza asked me to share some of my current research at the University of Texas. And of course, we're moving like others into the energy transition. So I started to work on hydrogen, and of course, continue working on CCS, CCUS, in addition to EOR. So with that, I'd like to start my presentation with this introduction, that how the oil and gas industry can contribute to a lower carbon future. So there are different ways that we can contribute and achieve this lower carbon future. There are countries that they're taking different approaches, reflecting their unique demand dynamics, capabilities, and cultures. And throughout these energy transitions, oil and gas will remain important part of the energy mix to meeting the global energy demand affordably and reliably, while contributing towards international climate agreement goals. So if you look at all the literature on net zero and lower carbon future, you will see that renewable energy is a key technology for the 21st century to be able to respond to the shortages in resource and also climate change. And on top of this list of renewables, you will see wind, solar, and geothermal. Also, the carbon capture and storage, CCS, and carbon capture and utilization and storage, CCUS, and have very critical role in a lower carbon emission future. We already know there are some large scale CCS, CCUS going on, and it is a reality. There are good geological formations. We know the engineering aspect of it and the commercial expertise to conduct these type of projects. Existing infrastructures, pipelines, and known geological formations can also be used for transport and storage of CO2. Another component of net zero is clean hydrogen. It used to be called green hydrogen, but even Department of Energy has changed that to clean hydrogen. So even if you produce hydrogen from SMR, as long as you include the CO2 storage, then it will be considered clean. And is a very versatile, clean energy source. And many publications, they describe hydrogen as a missing link in effort to make energy system radially cleaner. Hydrogen has lower costs than total electrification. There are sectors that you cannot decarbonize, or is not easy to decarbonize with electrification. So hydrogen might be a good solution. And there are ways to store or transport excess renewable electricity production. So if you have excess energy from wind or solar, you can convert it to hydrogen and then store it. And it's actually a way to continue to use the gas network infrastructure. So all the natural gas and gas infrastructures that we have can be used, maybe with some modifications, for hydrogen. So a little bit of activities in CCUS and hydrogen. And of course, you see the activities are increasing in terms of the capacity in megatons per year. It's been increasing. But if you look at the trend in 2022, we still need to increase the capacity by almost 8 times in order to meet the 1.5 degree scenario by 2050. And for hydrogen, including the electrolysis and other types of hydrogen production, the capacity has been increasing since 2019, but we're still short by almost 7 times to meet the net zero. So we need more projects on both CCUS and hydrogen to meet the net zero target. So my research currently focusing on modeling and simulations of CO2 and hydrogen storage in geological porous media. So first, I'm going to start with CCS and why we need to model and predict the long-term security of CO2 that is stored in subsurface, and how can we store CO2 in subsurface. There are different mechanisms for almost permanently storing CO2 in geological formations. One is the dissolution of CO2 into the brine, and that's the most secure form of storage. And of course, this dissolution depends on a lot of factors that we're going to talk about it. And that's why you really require phase behavior, equation of state, in order to capture the changes in the properties of CO2 as a function of pressure and temperature for different scenarios. Another storage mechanism is the residual trapping. And all of us, we're familiar with that in petroleum industry. When you do water flooding, you're going to leave some of the oil as a residual that is going to be very difficult to mobilize. So that will be another mechanism that require, again, multi-phase flow and also knowledge of petrophysical properties like relative permeability and capillary pressure, possibly hysteresis. Geochemical and mineralization is also very critical, especially for long term, and that requires modeling of reactions and geochemical reactions. And there are groups now that they're trying to expedite the mineralization of CO2 by adding some chemicals or maybe changing the composition of the brine to, again, expedite the mineralization. Like any other project that requires injection in the subsurface, you need to be aware of the geomechanics due to the injection of very large volume of the CO2 and possibly forming hydrates, ice, that may cause some fracture initiation. So you need to also look at geomechanical modeling in your CO2 storage projects. CO2 has relatively complex behavior. In terms of the phase behavior as a function of pressure and temperature, you can actually form solid, which is the hydrate. And we need to be concerned about it in some of our projects, especially when you have depleted gas reservoirs with a low pressure. You can form a gaseous CO2 in subsurface, or if you are beyond critical point, you can have liquid CO2, so-called supercritical CO2. So that transition of the phase behavior of CO2 and corresponding properties of it is very critical when we're looking at CO2 EOR or CO2 storage in aquifer or depleted reservoirs. Viscosity is a function of temperature and pressure. Similar to the liquids, it will go down with increasing temperature and it increases with increasing pressure. Density is a function of pressure and temperature, and all of these, they need to be calibrated for your specific case that you're trying to model. Another property, maybe for those that they've been doing CO2 EOR, they're not paying attention to it as much, but that is the solubility of CO2 into the water as a function of salinity. And there are data in the literature available that CO2 solubility decreases as you increase the salinity. Solubility is also a function of temperature and pressure. So the higher the temperature, the lower the solubility. The higher the pressure, the higher the solubility. So when you increase the pressure, actually you're becoming more miscible. So you solubilize more CO2 into the brine. So I'd like to show you, there are a lot of ways that you can calculate or estimate the capacity of CO2, either in saline aquifers or in depleted oil and gas reservoirs. And some of the challenges with CCS and CCUS is the injectivity, how to predict what the injectivity of CO2 is going to be, estimate of its capacity, and containment. You don't want the CO2 that you're storing is going to escape or leak. So these are very critical. And capacity, there are different softwares and different methods that you can estimate the capacity of CO2, again, in saline aquifers, which is this plot, versus oil and gas reservoirs. One is a very simple static estimate. So you're not including any of the dynamic effects of injectivity or heterogeneity. There are two estimates from Department of Energy versus USGS that you see they're widely different in terms of the capacity for different, low, medium, high scenarios. And if you look at the oil and gas, same story. The estimates, they're very different. And it's interesting to look at this, that the estimate of capacity, total capacity of CO2 in oil and gas reservoirs in US is almost 100 of the total capacity for saline aquifers. So saline aquifers, they can provide much larger capacity, at least based on the estimate that they have. But I like to show you that in reality, things will not work as we do these simple estimates of the capacity or injectivity. And one example is the Snowbit carbon storage project in Norway, that they were planning to inject in a lower zone in the reservoir tubing. And after injecting about 1 million ton, they start to pressurize the reservoir. And that's why they ended up shutting this zone and then start injecting in the upper formation. And since then, they've been successful and they have injected 4 million tons since 2008. So again, based on modeling predictions, what the reality was far from what they predicted. So that's why we're trying to do field demonstrations and experiments to learn from them, and then also help us to calibrate our reservoir models for better predictions of the future storage projects. So the purpose of the field experiments are to demonstrate that CO2 can be injected in, for example, saline formation without any issues on health, safety, or environmental effects, and determine the distribution of CO2 using some monitoring techniques. So monitoring surveillance is critical for CCS projects, and validate the conceptual and numerical models and gain experience for future larger scale projects. One of these experiments was the one done in Frio, US Gulf Coast, where the University of Texas Bureau of Economic Geology was involved. And then we also, once we had access to the data, we were trying to model this CO2 injection in the Frio aquifer. It was a small test. There was one injector and a monitoring well which was about 30 meters away. Actually, this is the picture of Frio, and this is where the injection well is. Maybe somewhere here, where probably Suhawarka is sitting there, is the monitoring location. And CO2 was delivered in a tank as a liquid. Reservoir is about 57 degrees C, with some dipping, 5 to 25 degree, and 1,600 tons of CO2 was injected in a period of 12 days. And of course, we were trying to simulate this test. This is one of the realizations of the model, showing the porosity. And there were some faults as well here. And these are showing the location of the injection well and the observation well. In some of our simulations, we did not include the effect of temperature, even though when you're injecting CO2 in a liquid form, it's cold. And if its formation is warm, you're going to have a distribution of temperature around the wellbore. But we did not include it initially, but later on we had temperature turned on. No geomechanics and no geochemistry initially. And again, later on, we added some of the reactions that they did measure based on the produced water and the minerals in the laboratory. This is many people, different groups, they history matched or modeled this test, including the group at the University of Texas. And this is one in 2017 by Dr. Wheeler and her group. This graph shows the green is the rate, the injection rate. This should be rate. And of course, we modeled that correctly in the simulator, what the actual field was. And the only thing really you measure is the pressure response. So these points, they're the pressure that was measured, and the solid, the simulation sort of history match. The important part of the CO2 storage is having an idea about the plume and the extent of it, because based on numerical simulations and knowing how far the CO2 plume is going to move is going to help for the planning of the monitoring and type of tests that they're going to do, and different sensors to monitor the test. So this is very critical to provide this kind of information to the field guys and people that they're doing the monitoring and surveillance. For example, this is, so when you inject CO2, it's going to move up, is like any other gas, and is going to accumulate below the seal, that's called the plume. And after the injection stops, the plume is going to continue moving till it becomes completely residual or mineralized, and that point is going to stop. So this plume here is right, this is the observation well, this is the injection well, and this is right after the end of the injection. And 10 days after, you see the plume is moving upward below the seal, and is going to get diluted, the saturation or the concentration. This is after 30 days, and 60 days already moved about 300 feet from where you injected. So you see that plume is going to continuously moving and eventually is going to get completely stationary. Another test was Cranfield. Again, University of Texas was involved in doing this demonstration test. And Cranfield in Mississippi is very deep formation, relatively low permeability, but heterogeneous, high temperature, and high salinity. And this was a little bit larger test. They injected about 1 million metric tons per year, and total injection rate was about 5 to 10 million standard cubic feet per day. Cranfield is part of an EOR, CO2 EOR activity. So this is where the CO2 EOR high rate injection was going on. And then this smaller area is where they did the CO2 injection into deeper formation, which is the saline aquifer. One injection well, that's the injection zone, and 2 monitoring wells. The first one is about 200 feet away from the injector, and the other one is about 300 feet from the injector. And there were a lot of different monitoring, taking samples, pressure, temperature, composition, and so on going on during the test. This is the site. This is the injector. And I believe this was one of the monitoring wells, and this was the second monitoring well. And again, we try to simulate this and history match the response of CO2 injection into Cranfield. This is the entire model, and CO2 saturation after 3 years of injection. This is actually where the CO2 for storage was done. These are CO2 for EOR. And after 10 years, so 3 years of injection and 10 years of redistribution, most of the CO2 is gone up to the top level. That's a top layer, and distributed aerially. If you look at the cross section, this is after the injection. And now after distribution, most of the CO2 just moved up to the top layer. Again, this is the injection rate. So it was variable. They didn't keep it constant. Initially, they tried to keep the rate, ramping it up gradually. So they started with about 200 kilogram per minute. Then they increased it to about 350. Then they almost, doubled the rate from the initial. And then they backed down the rate. And I will tell you the story, what happened there. So this is the pressure, bottom hole pressure. Red, they're the field data. And the blue is the first set of simulations that we did. And nicely, we matched the pressure response up to the point that they increased the rate significantly. So we had a hard time to match the pressure drop with the original conditions that we had. So the only way we could match the pressure is to increase the permeability near the injection well, sort of like you may have created some small fractures that causes the pressure response to be lower. And later on, they actually admitted that there was some fracture initiation due to the injection of CO2. And it was mainly because they increased the rate. We also looked at the effect of grid. And here with the coarse model, it was about 200 feet by 200 feet by 4 feet, the grid sizes. So these are really large, lot of numerical dispersion that it will impact your plume and results. But when we did grid refinement, very fine grids, you can compare actually on the zoom in graph, the plume with the grid refinement versus original coarse grid. So again, this is very critical to know the extent of the plume, again, for your monitoring and surveillance activities. So I'm going to summarize on CCS, CCUS, based on what I've learned. I believe still the prediction, accurate prediction of CO2 fate is a challenge. And CO2 storage models, they're needed for both laboratory scale and large field demonstrations. And I think we still need to do some laboratory experiments. Modeling is an iterative and dynamic process, and constant updating of the dynamic model is needed as more data becomes available from the field or from the lab. It is important to have a computational environment that allows for easy incorporation of different physical models, as well as the ability to apply high performance computing power to run large fine grid models and large temporal scale, like for more than 100 years of simulations. So again, I think there are still room for improvement of our modeling and simulations in this area. Next, I'd like to talk about hydrogen. So all of you, I'm sure, keeping up with the news, and the world is actively switching to energies with lower carbon emission, and hydrogen is attractive for power generation and offers both reduced emissions and increased energy security. Hydrogen is an energy carrier and a versatile source of energy. You can use it for different applications. It has the highest energy content by weight compared to other fuels. For example, 3 times of gasoline. Liquid hydrogen can be used in space, maritime, aviation industries, and road transport sectors. So again, very diverse. Hydrogen production costs and storage are keys to full hydrogen economy. So if we can produce it at a lower cost and be able to store it at a reasonable cost, I think we're going to have more expansion of hydrogen. So what are the current storage options for hydrogen? You can have surface tanks, and there are some places that there's still, if it's a small production, you can keep them in surface tanks. Some portable cylinders for liquid and gaseous hydrogen. So you've seen some, pumps that they have hydrogen and they're in a form of cylinders. Salt caverns and line caverns. And there are already 3 examples of hydrogen storage in salt cavern in Texas. Saline aquifers and depleted oil and gas reservoirs. And if you're not familiar with hydrogen, there are a lot of industries that they can actually use hydrogen. And you can use it for power generation and storage. You can use it for transport, especially heavy trucks, and also heating, including district heating. So clean hydrogen, along with other low carbon technologies, is key for a clean and secure energy future. So my interest, I started with looking at storage of hydrogen and looking at saline aquifers versus depleted oil and gas reservoirs. So that's how I started the research in this area. And of course, there are a lot of requirements for hydrogen storage in subsurface. What you're trying to do is hydrogen should stay in place and in a confined volume. It's different than CO2 storage, because here you want to inject and be able to produce back. It's a commodity. And these might be like, in week type cycles versus maybe month cycle, depending on the demand at the time. You're looking for large storage capacities, especially for those that, you're trying to store it for a longer period of time and then produce them back on a seasonal basis. You have to be able to produce most of the CO2 that hydrogen that you injected with minimal losses. Very little leakage and dispersion, of course. And be able to produce hydrogen at high enough rate to meet the demand and the power load balancing. So you have to be able to rely on how much you can produce and convert to the power electricity. Minimal impact of geomechanics, because you're constantly injecting and producing in these cycles, and the rates might be high. So you want to make sure that you don't have any issues. So geomechanics become very important. You need to be close to cost-effective, close to facilities that you have already, so to minimize the transport. And the usage should be close by again for minimizing the transport and distribution cost. And keep in mind that hydrogen has very different properties than the gases that we're used to compared to methane and CO2, for example. This is an example of the density versus pressure and, of course, temperature. And you see that hydrogen has much lower density compared to methane or CO2 for a wide range of pressures. So its movement and transport in subsurface is going to be different than the other gases. So then, again, I started to take some of the models that we had in saline aquifers that they were used for CO2 injection, and also some of the depleted oil and gas reservoirs that we had for example, EOR, and try to get some understanding of pros and cons of each of these options. So this is just more very high level pros and cons of saline aquifer versus depleted oil and gas reservoirs. So for saline aquifers, it's two-phase flow. So you have hydrogen and water, so relatively simpler. But the problem is you don't know the reservoir is not characterized like oil and gas reservoirs. No proven trap, so you have to make sure that there is, the trap that you don't lose the hydrogen outside the reservoir. You need to drill new wells, no infrastructure in terms of pipelines, production facilities, separation, hydration, and so on. But hydrogen might be relatively pure if you don't have biogeochemical interactions that may cause impurities in the hydrogen. So after you remove the water, dehydration, then hydrogen is going to be pure. Modeling and simulation is going to be simpler if it's just hydrogen in saline aquifers. On the other hand, for depleted gas and oil reservoirs, you have water, oil, and mix of gases. So it's going to be a three-phase flow. But you have extensive characterization. And by field projects, you already demonstrated that you have the trap. You have wells that may need to be modified, or you may have to drill new wells, but at least, there might be some wells available for these activities. Existing infrastructures. But then you have to worry about the legacy wells, possibility of leakage, and so on. Hydrogen is going to have impurities. So if it's in the natural gas reservoirs, then you may have other gases, methane, for example, coming out with hydrogen. And that's something we're looking at least numerically right now. And the simulations are going to be more complex. Phase behavior and keeping track of different components will be more difficult than hydrogen in aquifers. And of course, we need to also compare geochemical and biological reactions for each cases, and the loss of hydrogen to hydrocarbon or water versus just only water in aquifers, and the cushion gas volume. So these are the topics that we're just started to look into more and more, but there are a lot of other things that we have to be concerned about. So the key factors in hydrogen seasonal storage, like all the reservoir engineers, they know that first you have to characterize the reservoir. So you need to know all the properties of the reservoir. You need to know the properties. And currently we're using a compositional equation of state for that, but there might be ways to simplify the problem. Petrophysical properties, relative perm capillary pressure, wettability, mobility, hysteresis. And then we need to think about, is this a long-term storage or is it seasonal? Because the way you optimize it and you do your operations may change depending on the needs of the storage. You need to think about operations. How many wells do you want to have? What are the designs of the wells? What is the injection extraction strategies? And then do you want to use different cushion gas, for example? And more and more people working on hydrogen, they're more concerned about geochemical reactions, geochemicals or biological reactions, and also geomechanics. So we have to keep all of this in mind when we're looking at the laboratory or modeling aspects of hydrogen. Here, I'm just highlighting some of the key properties of hydrogen versus temperature, pressure, and salinity. So density, once again, very low density compared to methane or CO2 as a function of very wide range of pressures. Viscosity also hydrogen has a lower viscosity compared to other gases, and it is also dependent on pressure and to some degree to temperature. Solubility in brine versus pressure, relatively small, is not as much as what we have for CO2, but we need to consider that because that solubility may promote some reactions with the minerals. Interfacial tension is much higher than other gases with water. So hydrogen is up here, this is methane, and this is CO2. So in a way, almost immiscible. And with changing the temperature and pressure really doesn't change significantly the interfacial tension. Relative permeability and capillary pressure also very important. More data, they're coming out as we speak. And the first data set was from Yekta in 2018. He measured the hydrogen water relative permeabilities at 2 different temperatures and 2 different pressures, and you cannot tell the difference. So it seems like within that range of temperature and pressure, no impact on relative permeability of hydrogen and water. Also, from another reference, they compared hydrogen relative permeability from Yekta's, it's actually exact same curve, versus CO2 and methane. And you see that hydrogen relative permeability is much smaller than CO2 and methane. Of course, you have pressure differences, you have temperature differences, but it seems like you have a lower relative perm for hydrogen. Okay, so now I mentioned FREO, and FREO is the one that was used for CO2 injection in saline aquifer. That's in actually close to Houston, the location. And I took that model and I said, okay, let's just use that for hydrogen injection and see what happens. And of course, we ended up with a lot of more simulations because we realized that we have to do more optimizations in terms of the location of the injectors. If we need more production wells, because a lot of times, I'm not including cost here, but you might be able to have a better response if you inject, produce from the same well, but then have additional wells versus just one well that injects and produce. So it seems like you're going to have a better responses if you have more wells for production. We also looked at different cycles, like, 120 days injection, 120 days production versus 60 days. So a lot of different scenarios. And then at the end, we were looking at the working gas. Working gas is the volume of the hydrogen that you can actually produce and be able to sell it or convert it to power versus cushion gas. Cushion gas is basically a loss. Whatever is going to remain in the formation. So we're looking for higher working gas, a lower cushion gas as an optimum case. So for all the cases that we ran, the blue is the working gas and the red is the cushion gas. You see quite a bit of variation depending on your sensitivities and the number of wells and so on. And then this is the actual model. And we moved the injector from the location where CO2 was injected because it seemed like it makes more sense for hydrogen injection due to its lower density and lower viscosity. So it's more mobile than CO2. So normally we look at the cumulative hydrogen injected versus time, cumulative produced, and the cushion volume, which is the difference of these two. So you see that over the cycles, we're increasing the volume of hydrogen, and relatively cushion gas remains steady. If you look at the injected and produced hydrogen, initially with the initial cycles, this is the third cycle, is pretty small because you just started to inject and fill up the formation and produce back. As you add more and more cycles, of course, you're going to have more production of hydrogen. So here is actually pretty good volume. And the recovery factor corresponds to the injected and produced. Initially, maybe 80% of hydrogen is recovered, but then over time, we get to almost 90% recovery. And this is in saline aquifer, but required some optimization. And then the storage in depleted oil reservoir. This is a case that we had that was considered for natural gas storage, was a depleted water-flooded oil reservoir, but then a company was considering this as a natural gas storage. So we already had some experience modeling natural gas. Then we used this and converted it to hydrogen injection. For the natural gas, the design was to have 9 vertical injectors that they also produce back in layers 5 and 6, so the bottom layers of the reservoir, and 15 vertical pump wells. So these are the wells, is basically like a producer, additional producer. And the purpose of these for the natural gas project was to produce water, so then you have more space for natural gas to be stored, increasing the capacity of natural gas. And this formation has an interesting, characterization. This is a very high permeability channel, and that's a dome, and with surrounded by low permeability, about 10 millidarcy. And of course, there were aquifers on 3 sides of the reservoir maintaining the pressure. So it's a very complex case, I think, we started with. And this scenario for natural gas strategy was to fill up the formation for 12 months of injection and 6 months of production, and then start the cycling injection and extraction, 3 months injection and 3 months production for almost about 5 years. So it was very interesting comparing natural gas and hydrogen, again, keeping everything the same. All we did, we just changed the natural gas to hydrogen for this case. And this is the gas saturation at the last cycle. Hydrogen, it just moved through the channel, the high permeability channel, but natural gas is more confined. And if you look at the volumes that was stored, hydrogen was much lower than the natural gas because we weren't able to inject as high rate of the natural gas, again, because of the properties of the hydrogen. So we realized that we have 10% less hydrogen compared to natural gas, 32% less working gas capacity, and we also even produce less oil, and 3% higher saturation in the top layer for hydrogen. And that's why we started to change the strategy for hydrogen, try to optimize it for this case. A lot of activities on hydrogen. I'm not going to go over all of them, but recently, for example, the gas blending, so be able to combine hydrogen with the natural gas. Sandia National Lab has a project. Australia, they have a project. And also in San Diego, California, in addition to some of the storage in saline aquifers, in depleted gas reservoirs, or in salt caverns, like the one in Mississippi is going to be in 3 salt caverns. So in summary, for hydrogen, saline aquifers and depleted oil and gas reservoirs provide large storage volumes and deliverability. But you need to optimize injection and production strategies for each site for cost efficiency. More research is also needed to evaluate loss mechanisms in each site and contamination levels of produced hydrogen, because all of this basically will be economically unfavorable. We need more simulation studies and analysis on cushion gas for depleted gas reservoirs and compare with depleted oil reservoirs and saline aquifers. Again, we're looking at potentially nitrogen, maybe CO2 as the cushion gas rather than natural gas or hydrogen, that they're more expensive. So now on the production of energy, I'm not going to spend too much time. You guys know that I've been working on EOR for a long time, especially chemical EOR. Still, there are companies that they're looking at, especially polymer flooding and ASP. So I like to talk a little bit about those activities at UT right now. So anytime you're planning an EOR project, of course, you're going to go through stages. You do high-level screening, then you do feasibility studies, then you do numerical simulation, project optimization, and eventually facilities and surveillance. But and I put bullets for each of these, and I'd be happy to share these slides with you. But the key is, in every step, every stage, you need to collect data, and you need to also include numerical simulation. So that's the point I have on this slide. So what are the success criteria for EOR projects? Number one, you need to be able to inject at the desired rate and under matrix conditions. Most of the time, you don't want to create fracture, and injectivity is going to basically impact your economics. So you need to be able to inject as fast as you can. Ability to achieve oil response by managing sweep efficiency and conformance. Demonstrate commercial feasibility of scale up to the full field. And ability to acquire monitoring and surveillance data. So to me, the most challenging question as of today, are EOR simulations predictive? Can you convince decision makers to make large investments based on forecasting simulation results? Do we have all the critical data needed at lab and field scale for mechanistic and closer to reality type simulations? I'm not convinced that we're there yet. And of course, we try to do laboratory experiments. These are for phase behavior with surfactant. Then we do core floods. We may do many core floods. Then we go to the field and we do a single well test to see the response of our EOR strategy. Then we do the pilots with multi-wells, and then eventually we go to full field. So data collection and numerical simulations in every step of the way. So my talk, I'm going to focus on polymer and surfactant polymer flooding, or possibly ASP. But there are a lot of hybrid EOR methods that trying to make the process more efficient and more cost effective. And when you do hybrid methods, then your modeling is going to become more challenging and complex, because now you need to combine different mechanisms for different EOR production mechanisms. So some examples of Mangala ASP. This started in the lab at UT, doing laboratory experiments, developing formulations. And of course, they did a very successful pilot a 5-well pilot, a 5-spot, and then they went to full field polymer project, and now they're planning for larger ASP. It may happen in 2023. So that project still continues. And we were involved in laboratory studies. We were involved in the simulation. These are some of the examples of our UTChem simulations. And also somehow we're involved in the larger scale implementation. The other test is the ASP in carbonate reservoirs in Kuwait. And of course, we were involved in developing the formulation. We history match, and we were there when they were doing the single well injection to know the response of the ASP formulation. We modeled the reservoir and so on. And it was pretty successful. The single well test showed about 33 saturation units was recovered with the formulation. So that shows about 90% recovery of the water flood residual oil saturation. And numerical simulation was critical for this single well test in a very unconventional reservoir, because the field is very heterogeneous, is very thick, and it was not confined. So the normal design of the single well tracer test did not work here, and numerical simulation guided the company to change the way that they're doing the second tracer test. So that was very interesting. Then I have a student right now that we were interested in collecting a lot of data from different commercial labs and from the University of Texas measurements on the polymer rheology. So when you measure the viscosity of polymer solution as a function of shear rate, that's the normal behavior. So we collected about 10,000 data points for different polymers, AN125, SAV10, and 2 FlowPAM products, for a wide range of concentration of polymer, wide ranges of salinity, hardness, and temperature. And spend a lot of time to QC the data. And then after all of the removal of duplicates, problem data, then we ended up with 250 types of curves here with different polymers. And using the concept of physics-based and data-driven science, we ended up with the correlation, is basically an empirical correlation for modeling the viscosity of polymer as a function of concentration, salinity, hardness, temperature, and so on. And then we implemented this correlation into UTChem. It makes it so much easier. You don't need to calibrate your original default model with every data points that you have available. Everything is already set up, and we're making comparison with the original models right now. So for the CUR simulation, there are still challenges remaining and still evolving. Accurate models of microemulsion phase behavior as a function of temperature, pressure, solution gas, co-solvent, salinity, and hardness. I don't think so we have the answer to all of this after all these years of doing experimental work and simulation. We still need to understand our 4-phase relative permeability and capillary pressure when you have all these four phases flowing. And then discontinuity issues. When one phase disappears and one phase shows up, that will cause a lot of numerical issues. Fluid properties, they also need to be a function of composition, pressure, temperature, co-solvent, salinity, and hardness. Again, we're making improvements, but I don't think so it's perfect. How do we upscale from lab scale to field scale? That's a remaining challenge for every topic that we're working on. For hydrogen, if you do micromodel experiments, when you do core flood experiments, how do you upscale to the field? chemical EOR in naturally fractured reservoirs, and what is that matrix fracture transfer. Very important for flow assurance and for some of the mitigation strategies to couple the wellbore to reservoir, to be able to predict what the emulsion you're going to produce in the producer wellbore, what kind of scale, and can we come up with some mitigation strategies. Breaking the emulsion and prediction of emulsion is a very expensive and scary topic for surfactant and polymer floods. Geomechanics and pressure-induced fracture initiation and propagation for polymer, foam, and conformance control methods. Again, many groups are trying to improve their understanding, but I think we need to have more data from the field to be able to understand what happens under what conditions we will have these fracture initiation. So with that, I'm going to complete my talk. And these are some of the companies supporting reservoir simulation, JIP, and I'll be happy to answer any questions.
Thank you so much for such a great presentation. Excellent. I encourage audience, if they want to ask question, they can unmute themselves and ask the question. Also, I place a question from Dr. Ding. Also, Dr. Ding, maybe you can unmute yourself if you want to ask your question. Also, Dr. Delshad, you can see Dr. Ding's question, or maybe I can read for you.
Yeah, you can read it for me, or
okay.
if you want, I can. Yeah, I've seen a lot of familiar names, so super. Hi to everyone I know, and it's great to see them.
Dr. Ding.
Let me start asking you a question. This is Tawed Agani. I'm a retired Chevron Emeritus Fellow. Now, just resting. But thank you very much, Dr. Delshad, for very insightful presentation. I really enjoyed it. I have a general question in regard to CCUS part of the presentation. That U part of the CCUS is a main factor right now that makes these, I guess, projects economical or not. I mean, just CCS part of it probably are justified based on tax credit or, or carbon credit or some intangible benefit that oil companies get out of it. But the utilization part of it, I suppose, I guess, combination of CO2 storage and EOR and optimization of how much CO2 you can store at the end versus how much oil you can produce should be, I guess, the main factor. So this is one question. And the second question, I don't know if it was a comment or a question, but it was a comment. But the question I have, okay, according to your experience, when you're dealing with CCUS or storage of hydrogen, I guess, there are inherent uncertainties associated with any subsurface process, as you're aware. And most of these studies have to be done within the context of uncertainty. According to your experience, what is of course, it depends on the reservoir setting, but what's the most uncertainty parameter that you are concerned about when it comes to CCUS?
For hydrogen?
No, just for carbon storage.
Oh, okay, yeah. Well, first regarding your comment, absolutely, you're right. Right now, if you have tax credit or some sort of, exchange of the carbon, that's the only way that you make money on CCS. So utilization is very important. And actually, I'm still involved in some projects that they're thinking about injecting CO2 that is captured and produce whatever oil they have, and then continue with the CO2 for storage. So in terms of modeling, I'm trying to do co-optimization of EOR and storage. And there are a lot of things that you can do there as well to maximize the production and also maximize the storage. So that's an area that I'm still working on. In terms of your second question, the most uncertain parameter, I think even today, I think is the reservoir characterization and the cap rock integrity.
Yeah.
And that's what, yeah.
Yeah, exactly. Yeah, you're right. But again, these projects are designed, yes, for long term. I mean,
Yes.
we're talking about hundreds of years.
Yes.
Okay. And I'm assuming that monitoring
Yes.
of, is a really critical issue. And how would, I guess, monitoring, you can always do the monitoring in a short scale of time, like, whatever, in years, but not in hundreds of years. So,
yeah.
I mean, somehow, again, that uncertainty calculation or, coming up with a range of forecasts that where the plume is moving and how much you're storing because of solubility, how much you're storing because of capillary trapping, or or free phase or whatever, has to be done.
Yes, there was I don't remember the name of the project, but there is one in Australia that they injected CO2 and they're monitoring it now. I think it's almost 10 years. Of course, some companies, they're coming up with the faster and cheaper way of doing seismic. So you can go back and just do another seismic testing to help you what is going on. And depending on the location where you are, if the surface is clear, then you might be able to do, the satellite drone type of testing to see if you see the surface is elevated or not. So they're coming up with a cheaper, faster way of monitoring for a longer time. So that technology is also improving, but it's really hard to predict where the CO2 is going to go. It's going to be hard to predict where the hydrogen is going to go. And for hydrogen, even is more critical because you want to produce it back. So uncertainty, that needs to be, and that's what a lot of groups are doing, what are the impacts? What are the, I just did one for a potential test of hydrogen in single well in a shallow aquifer. And we started to look at what if the dip angle is not like, constant dip, the surface goes up and down. That will impact your plume. What is the impact of KVKH? So it just became a huge project of just looking at uncertainty because they wanted to know where to put their monitoring, sensors.
Again, thank you.
Sure.
Could we have a copy of your slide deck, or these are confidential?
No, I can, nothing confidential at the university. So I'd be happy to share with you, Kaveh. Thank you.
Thank you very much.
We have a couple of questions. I try to read them.
Sure.
Question, Rocky from the Aramco. I have two questions about the CCUS. What is the wettability of the CO2 under typical reservoir condition? How can the reservoir simulators distinguish between the supercritical / liquid CO2 and the hydrocarbon phase, given that their densities are similar?
Well, for CO2, the wettability, of course, a lot of data available for contact angle wettability, CO2 in carbonates versus CO2 in sandstone reservoir. So that information is available. And then, of course, with your petrophysical properties, you can change your relative permeability and capillary pressure accordingly. The other question is more important. Let me
maybe I can.
Read it again for me so I'll make sure.
How can the reservoir simulators distinguish between supercritical liquid CO2 and the hydrocarbon phase?
Yeah, so basically, you have to be very careful about doing that. The commercial reservoir simulators, they use density to distinguish the two phases. But in our in-house code, we have different options of distinguishing the phases. And that is still a critical part of the equation of state when you have fluids that they have very similar properties. Good question. Good one.
Next question. Would you please explain a little bit about the line caverns? What is the line cavern that you said?
Yeah, so there are the caverns, different types of, actually I'm learning about them. You know, there are the ones that they have more heterogeneity in them, the embedded, you know, they call them, I think, caverns versus the salt caverns that they're just sort of more uniform in terms of you don't see much of heterogeneity, much of composition changes, and you just dissolve the salt and then you have a very nice cavern. But the other ones, they're bigger, they're larger, but they're more complex in terms of the storage. Today, most of the groups that they're looking at hydrogen or natural gas storage are looking at the salt caverns. They're easier to make them and easier to store.
As a last question, how do you see the future of the CCUS and hydrogen storage and EOR specifically in US and the rest of the world as you work a lot in this field?
Well, I think the activities in the US in EOR has been very, very, even before this energy transition, before, COVID, was very small. It was mainly focused on CO2 EOR. And the reason it was CO2 EOR because we have access to cheap sources of CO2, natural sources of CO2, and we already had the infrastructure, the pipeline. That's why CO2 EOR became number one EOR in US and in the world. Chemical EOR, pretty much activities almost zero in US, maybe small polymer projects here and there, but nothing significant. Thermal projects in California, overall, they started to go down because of all the environmental aspects in California and water issues and carbon issues and so on. So EOR in US, I think the only thing may stay is the CO2 EOR may continue for a while. Or they may look at CO2 injection into unconventional. So then you can increase the production in shale. At the same time, you might be able to get credit for storing the CO2 in the shale plays. Around the world, that's a different story. Still, they need oil, they need fossil fuel, and not necessarily they're all ready to jump into hydrogen or to just CCS. So they will continue possibly CO2 EOR, polymer flood. There are projects going on still in the Middle East and South America with polymer and surfactant floods. And then once the CO2, they can capture it and have more CO2, they can look into CO2 EOR plus unconventional. So I think oil and gas production, especially gas now, is going to continue for a while around the world.
Excellent. Just a very, very quick question from myself. Where is that natural CO2 pipeline that you said we have in the US?
Oh, you haven't seen that?
No.
I can send you the map. We've had very long pipelines, and it's a map of, I think it's from Department of Energy, that shows all the pipelines that they were used for CO2 EOR projects.
Oh, just designed for EOR, not for the other purposes.
No, it was mainly for, they were already there. So then when they were ready to do CO2 EOR, they could use that existing pipeline. Yes. And possibility of some of those pipelines may actually be retrofit for hydrogen, or the blend of hydrogen and natural gas, especially like in Texas. That's what they're considering. Yeah.
Excellent. Thank you so much. Thank you so much. I would love.
Thank you, Hamid Reza.
One more time, thank Dr. Delshad for accepting our invitation and for such an interesting presentation. And thank you all the participants for taking time and take part in this event. And I wish a very happy rest of the night. Thank you.
Thank you. Bye-bye.
Bye-bye.